So hopefully it's not too hard, but I'm glad it's the first lecture and you've probably just had your coffee in the morning. I'd like to start by saying thank you to Noam for inviting me here, and just thank you to the Gwangju Biennale for giving me the opportunity to speak on such a wonderful platform. So, as Noam said, I'm an artist and I also have a background in quantum physics. For those of you who don't know me, my art practice deals with quantum ontologies, the nature of existence and quantum versions of self. I've been working with IBM's cloud-based quantum computers since 2019. I write my own code, and this manifests across projection, gaming, playable environments, virtual reality, and some of these works also include quantum sound. Emotionality and embodiment are really important to me, and so is materiality. I also work with sculpture, notably glass, and more recently watercolor painting, thinking about the fluid nature of reality and how we intersect with it. But my work isn't really why I'm here today. I think Noam really wants me to sort of frame this symposium, as she said, through the lens of quantum physics. So before I went to art school, I had quite an adventure in the quantum world. I completed a PhD in quantum information science, and then also did 5 years of postdoctoral research at the University of Oxford and in the Centre for Quantum Technologies at the National University of Singapore. I published numerous papers on topics such as quantum entanglement, and I should say that I was a theoretical physicist, which means I worked with mathematics as opposed to in a lab with equipment. I'd probably break all of the equipment. It's probably why I'm better as an artist. But working with mathematics really allows you to start to see into the quantum world and understand what this reality might be. Of course, these models of quantum reality are just models, and we know how models are never quite match the actual object. So what is quantum mechanics, and why do we need it? So we live in a macroscopic world, which is described, as Noam mentioned, by Newtonian physics. So Newtonian physics is the physics of the everyday. If I throw this water across the stage, that would be the projectile that it would follow is described by Newtonian physics. It's the world of gravity. It's linear, there's cause and effect. Objects are seemingly boundaried and fixed. We can touch things. But this type of physics does not describe the microscopic world. We need a new type of physics. We need a new description of reality, and that description is quantum mechanics. And things get very, very weird very quickly. So quantum mechanics is a physical theory that describes a microscopic world. So then quite often people talk about it describes subatomic particles, but that's an outdated view. It also describes atoms, and sometimes now even molecules, how they interact and exchange energy. So we're always zooming down to the smallest parts of reality, and when you think in your mind about this, you might think that objects get really, really precise and point-like, like the tip of a pin, something very small. But this isn't what happens when you go small, and you also need to cool systems down close to absolute zero. So absolute zero is the coldest possible temperature of the universe. In centigrade, it's minus 273. I don't know what it is in Fahrenheit, sorry for those Americans here. And when you go cold and small, objects start to blossom. They become fluid and they actually spread out in space and time. They are no longer boundaried. They're plural. They're entangled. They're non-local. I'll explain this later. They're non-causal, and I would also say they're magical as well. So in some sense, going into the quantum world is little bit like Alice from Alice in Wonderland, falling down the rabbit hole and encountering a strange, counterintuitive, and sometimes even incomprehensible material reality, and that's what we're going to do today. Come with me. The Nobel laureate in physics, Richard Feynman, said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." And I can vouch, after many years of study, I do not understand quantum mechanics. I don't think anyone really does. So I'm not going to teach you quantum mechanics in a 40-minute lecture today. Rather, when I've spoken about this topic to other art audiences, they've often told me it sounds like poetry. So feel free to take what you want, treat it like poetry. And actually, I think it is quite productive to also sit in the unknown, which itself is very quantum. In some sense, quantum mechanics is a little bit like Plato's cave, where this is an image of Alice looking into Plato's cave and seeing shadows. So for a reminder of what Plato's cave is in this story, there's some prisoners who are trapped in a cave, and they're forced to face a wall where they can only see shadows. And this is their reality. This is their truth. The shadows are the truth. They have no access to their actual objects, the true reality that is behind them. So in some sense, the world we live in, this Newtonian reality, is like the shadows. But what we can do, and quantum reality are like the objects we don't have access to, but we can use mathematics and concepts from quantum physics to try to get closer into the strange quantum realities. So now I'm going to explain a few quantum phenomena to help you see how strange the quantum world is, and then we'll talk more about quantum sound. So you may have heard of quantum superposition, and this is when one material entity, so it could be an atom, it could be a molecule, is in two or more contradictory states simultaneously. So I'll explain a little bit more about this through some examples. One approximate analogy that I like to use is something called the Necker cube. So this Necker cube has two different perspectives at the same time. You can either see the face that faces bottom left appearing out of a page, or if you look, the other face, the square, might be coming out of a page top right. So this object has two different perspectives at the same time, but depending on how you look, you see one or the other. The liar's paradox is also an approximate way of understanding quantum superposition. So this sentence is false. So there's a paradox in this sentence, which means a contradiction, because the sentence says this sentence is, it means it exists, but at the same time, the semantic content of the sentence says that it is false. So at the same time, this sentence is both true and false. Obviously, these aren't material objects, but this is kind of how the materiality of quantum physics works. Now, because sound is bound up with time and space, I think it's also important to mention quantum temporalities. And to do this, we'll look at a very basic scientific setup called an interferometer. And these are used in labs by scientists to create superposition of individual particles being in two places at the same time. So what happens is, okay, So an individual atom goes into the system where it says input and hits something that splits it into going into two paths simultaneously. So one atom will take the top path, and at the same time, the same atom takes the bottom path. It's not that one atom splits into two. It really is in two different locations at once. And this is when you can start to see the entanglement of time and space. Each of these different paths has a different temporality, a different history. You can manipulate the atom in the reality that the atom is in the top path. You can even freeze time, whereas the atom the same atom which is in the lower path can experience a different time. So you have one object, you've broken the reality into two for it, like the multiverse, and each different path has a different temporality. The atom then combines again at the outputs. So it goes back to just being in one classical reality. We can also talk about quantum entanglement, which you may have heard of. Quantum entanglement is superposition for two or more entities. So quantum entanglement is when you have two atoms, or three atoms, or four atoms, etc., and they're connected in a way where all different possible ways of connecting exist at the same time. So quantum entanglement is a non-local connection, which means it can exist even if the particles are really far apart. So one atom could be here, and the other one could be in London, and they can still talk to each other, even if there's no substance that's helping them communicate in between. And this connection is stronger than anything described in the macroscopic world, in Newtonian physics. Another way of thinking about quantum entanglement is that it's a plurality of symbioses between two or more entities, atoms or molecules, that are so strong that it's impossible to tell the individuals apart. If you try to gain an individual from an entangled system, then you destroy the system. So for me, this is really interesting because like the whole of Western society is based on individualism, whereas this quantum entanglement kind of moves beyond the notion of individualism. So to see entanglement through superposition, through the Necker cube example, we can put two Necker cubes next to each other, and you can see that you always see the same perspective of both of the cubes. The perspective is either facing to the bottom left or it's facing to the bottom right, but never both at the same time. So you can see there's this simultaneous layering of reality where both possibilities exist at once. And this happens, like I say, even if the particles are really far apart. So what is the process of translation back to this Newtonian reality that we sense every day? And this is called quantum measurement, or we can also think about the interpretations of quantum mechanics. So we need to think about how we can start to access what is the relationship between the real objects and the images we see in this Newtonian reality. And it's actually still an open question in science as to how macroscopic reality emerges from the plural entangled quantum world. So there's many different interpretations of this. I call them belief systems because when we don't know really how, scientists interpret the mathematics, but they haven't tested them in experiments yet. They don't know how to do this. So in some sense, it's almost like religious systems. So two of the most popular interpretations of quantum mechanics are the Copenhagen interpretation, which is developed by Niels Bohr, and also the many worlds interpretation. So I'll start with the first one, which is Copenhagen interpretation, which is quantum measurement or collapse. So, to recap, how does the macroscopic Newtonian world emerge from the plural quantum reality of superposition and entanglement? So the act of measuring, which means recording information about a pre-materialized quantum state of superposition and entanglement by any entity, so that could be human or non-human, results in the indeterminate collapse of all possibilities to one possibility. So let's break this down. You have, on the left, the quantum superposition or entanglement. So this is a quantum reality. And something, a human or non-human, records information about this system. And then all of these different possibilities that exist, the layered realities, randomly collapse back down to one reality. And nothing in the universe can predict what this reality, like what outcome you'll get. It's genuinely random. So we're reducing all possibilities down to one possibility. So here we're still outside Plato's cave, and we're trying to understand what the real objects are, but we're getting kind of noisy information back out because of the randomness. Art critic James Elkins says that the paradox that quantum mechanics invariably presents to the intuition is that the physical reality proposed by the theory is both unpicturable and picturable. And that's because of this indeterminacy. He continues, the actual object in question, I would say, is inconceivable because it is only visualized by conceptualizing the unresolvable tension between what can and cannot be pictured. So in some sense, this process of translation from the quantum reality to the macroscopic reality is kind of impossible. It's really impossible to see or hear what is there, but we can try to get as close as possible. Now, I love this interpretation of quantum physics because it's the most creative. It sounds like science fiction, but it's not. This is the many worlds interpretation of quantum physics, which predicts the multiverse. So here, instead of being in Plato's cave, when we do not have access to the object, the real quantum object, we're going to dive into the quantum reality and try to understand what it looks like from within. So the many worlds interpretation of quantum mechanics says that a quantum event, so looking at the entangled layered superposition, leads, instead of collapsing it and leading to indeterminacy, it leads to a branching of realities. So both possibilities exist, but we only perceive ourselves to be in one branch of this. So this predicts a multiverse. So what I'm saying here is that when there's a quantum event, so when there's an event at the atomic level, what happens is the universe branches into 2 or 3 or 4. So what really exists is an infinite set of parallel universes of multiple times where I exist in some of these universes. In some of these universes, I haven't even been born. In some of the universes, Earth doesn't exist, etc. So all possibilities exist at once. And scientists love this description of reality because mathematically it's more elegant than the inserting randomness into the theory. So both of these interpretations of quantum mechanics fit, but scientists haven't found a way to test them in experiments yet. So we don't know which one is true or false. Maybe both are true somehow. So the multiverse you may have seen in this film, Everything Everywhere All at Once, which was an Oscar winner from a couple of years ago, where the protagonist exists across multiple possible realities simultaneously, and all of these realities are connected. So it could be that this is true, and I think this for me is one of the magical aspects of quantum mechanics and quantum physics. So going back to this setup where I was saying about how to create a superposition of a particle being in world 1 and world 2, the many-world interpretation is like the universe as split into these two branches. We're going inside this experiment. Now, this all sounds quite magical or strange or confusing, but scientists are using these phenomena, superposition and entanglement, to build new information processing technologies called quantum computers, and there's other technologies as well. And these are non-binary technologies based on the non-binary laws of quantum physics that I just showed you. I'm not going to go into quantum computing massively in this talk, but just to say, you can think of the basic unit of quantum information is called a qubit or a quantum bit, and this contrasts a digital bit. So if you think of a binary digital bit, it's 0 or 1. It's like a switch, on or off. Or it's like a coin, heads or tails. It can only be in one state at any moment in time. Whereas a quantum bit, because of superposition, can be 0 and 1 at the same time. So if we go back to the Necker cube example, this bottom corner here could be facing out of the screen, and that could be the 1 state. Or the 0 corner here could be facing out of the screen, and that could be your 0 state. And both of those can exist at once. And then using quantum technologies, you can create quantum entanglement. And when you create quantum entanglement within a quantum computer, the number of temporalities or the number of possibilities in the superposition expands exponentially. So you can see on the left here, I have 4 qubits, so squares are representing qubits now. And you can see how the different possibilities that are in the tree diagram expands rapidly, and so on. So as you increase the number of quantum bits, or if you increase the amount of information in the quantum computer, you get many, many different parallel realities, different layers in the superposition existing all at the same time. And this is what I've been working with in my practice. I've been working with quantum entanglement and understanding how we can edit video or create sound or do many other different things by exploring all of these different realities within the quantum computer by taking the multiverse, many-world approach. So I'm using techniques that allow me to bypass the randomness to really get inside these quantum possibilities. So here is an example of sound that I've made using one of IBM's quantum computers, and I've been sonifying entanglement. I think, yeah. I'll let you listen to it first, and then we can. So let me explain a bit. So that was the sonification of 3-qubit quantum entanglement. So there's 8 different possibilities, all existing at the same time in a layered superposition. If you had 3 digital bits, you would just have one note. There wouldn't be this melody, whereas because it's quantum entanglement, automatically you have this melody of sounds coming out because of quantum superposition and entanglement. So let me try and explain this a little bit clearer using an example from the movie Interstellar. So Interstellar is a film by Chris Nolan, and at the end, the protagonist, Marv, enters a higher dimensional quantum space as he flies inside a black hole. And he moves around in that space, and he encounters different versions of a scene with his daughter elsewhere that happened previously in the movie. So you can imagine inside a quantum computer, you have a high dimensional space, like those tree diagrams I showed you a couple of slides back. This is a high dimensional space. And what happens is, I build a quantum entanglement within the quantum computer, and then I'm moving around in the high dimensional space and listening to the different frequencies that are associated with the different layers of the superposition. So somehow I'm capturing the sounds of these specific types of entanglement there. So finally, I'm going to talk about the sound of quantum mechanics. So we've spoken a little bit about how I've sonified quantum entanglement using quantum computers, but does sound exist within the quantum world? And the answer is yes. And first of all, I'm going to recap what's the physics of sound in the Newtonian macroscopic world. So maybe you're familiar with this. There's a source, which is a red slider on the left. It could be the cone of a speaker. And there's a medium. And this here could be air, but it could also be water or a solid medium. But there needs to be some material substance there. And the action of the source on the medium causes a series of compressions and rarefactions, the spacing out of the medium. And that generates a wave. So as I'm speaking to you now, I'm speaking into the microphone, and then the speakers are doing exactly this here with the air in the room, and then you can hear me. It's important to note that there's many, many, many particles in the gas, in the air in this room, for instance. And each particle, you can see the red dots within the medium that's oscillating. The individual particles are just moving backwards and forwards. And they're only at one position in one instance. They're not in multiple different locations. This is Newtonian. And this is how we generate sound, and perhaps there's a listener at the end. But in the quantum world, there is sound, but it's very different. It's called phonon. And this is a scientific definition, but I'm going to unpack it in a moment. A phonon is a quantized unit of vibrational energy arising from oscillating periodic crystals. What does all that mean? So things are going to get weird again. As far as I know, no one has really written much about this in an art capacity, so bear with me and let's see if we can do this together. So what is a crystal? Well, you can think of a crystal as something like salt. Salt is a crystal, and the image on the left is an image of salt under a microscope. But we know quantum mechanics acts at the microscopic level, so we're going to zoom in even deeper to the microscopic level where you can see the crystal formed of atoms. So this is a crystal because it has a regular arrangement of atoms. It looks ordered. It doesn't look chaotic or random. And it's periodic because it's repeating itself. You've got a green atom, you have a blue atom, and so on. So this is where you can find quantum sound, in periodic crystals. Now, the thing to think about with solids, crystals, is that all of the atoms can be understood as being joined to their neighboring atoms through springs. So you can imagine the atom, each green atom is joined to a purple atom by a spring, much like how a car is joined to its wheel by a spring for its suspension. So the whole crystal can oscillate and vibrate. And we've already seen through the classical version of sound that sound is oscillation, sound is vibration. So this is still in the Newtonian world. So now we need to go down to cold temperatures, very, very cold, to understand what quantum sound could be like. So we're going to go back inside the quantum reality and understand how quantum sound could look in these crystals. So this is an example. I'm going to just take 5 atoms from this salt crystal as just a test case to help us understand it. So what you're seeing here is each of the red squares in the diagram on the left is an atom. There's just 5 atoms. Each vertical line represents 1 atom. But each atom is vibrating in a superposition of 5 different waves of moving. So remember, superposition is the layering of different realities simultaneously. So I could be here and in London at the same time. Well, here, each atom is vibrating with 5 different frequencies represented by the horizontal levels. Now, things get even stranger. When I hadn't really thought about the sound of phonons before Noam asked me to give this talk. So I went back to the mathematical equations to really get into my head, what does it sound like? And what I realized is that a phonon, the quantum unit of sound, has sound and no sound at the same time. And that kind of blew my mind. I went home and spoke to my partner. I was like, oh my God, there's sound and no sound at once. My mind, like even for me, see, I don't understand quantum mechanics. My mind is blown by it. So how does that work? So each of the different layers has a different frequency. So remember, the different horizontal layers are different layers in the superposition. So there's only 5 atoms, but each atom is vibrating with a different frequency at the same time. So 5 different things at once. So within the phonon, there's sound, but all of the different layers add up to having no sound. And this both exists at once. Maybe I'm going to repeat that. So there's a paradox there. Remember I said quantum mechanics is very paradoxical, and it helps us to understand how to live with paradox as well. So each layer in the superposition has a different temporality, a different sound, yet overall, the phonon, the quantum of sound, is atemporal. It sits outside of time, so therefore it has no sound. So it's different, but it's a little bit like noise-cancelling headphones. Now, noise-cancelling headphones are Newtonian. They exist in the macroscopic world. But you know, with noise-cancelling headphones, remember, if you've used them on an aeroplane, for example, there's the hum of the aeroplane. It senses the hum of the aeroplane, the sound from the plane, and then it plays the opposite sound to cancel that out. So then you have a quieter sensation within the headphones. So perhaps the quantum sound is a quantum version of this with superposition instead. And the final thing, well, there's 2 more things that I want to say. One of them is that what is the source of the quantum sound? And what I realized is there is no source. The medium is the source. The source is the fact when you cool the crystal down to absolute zero, the sound just erupts into being. It's playing itself, which I find quite interesting. So if you wanted to work with quantum sound, you could either approach scientists in the lab who are working with phonons in a university, or in the future, quantum computers, which are still currently in their infancy, they're not fully developed yet, will be able to simulate these phononic environments, these phononic crystals. So in the future, maybe 10, 20, 30 years, we'll be able to use these devices to access these shape-shifting plural quantum soundscapes. Thank you.
Wow. So thank you, Libby. I'm not sure even I know how to start. Yeah, I live in one time, but I have a few temporalities in my head now, and maybe we can start from something that is very basic. First, how much time do we have for this talk? 10 minutes, wonderful. So you said something that stayed with me, and maybe it's kind of like the knot that we can access this. You said that phonon is the superposition of vibration, right? So sound is a vibration, and a phonon would be a superposition of a number of those phonons, right? Those sound units. And then each one of them can move or have sound in different ways, right? Move in different directions. And I want to start by asking, can this even be audible or hearable to a human ear?
That's a good question. So obviously this exists at a microscopic level. The way I would approach this if I was to work with phonons was so depending on how you try to listen to the phonons, you're going to get different outcomes. You would get sometimes no sound or sound. And I do feel, so yes, what you could do is use amplification techniques. So how I sonified the entanglement with the quantum computer, you could do similar experiments, but with the phonons as well. So it's audible, but I can't imagine what it would sound like at the moment because I'm still getting my head around the sound and no sound at the same time. I think it depends on quantum mechanics is contextual, so how you listen shapes what you hear. Yeah. So one of the, there's so much in that talk already, I didn't mention it, but yeah, how you perceive reality changes reality. And I think that would be the same with the listening as well. How you listen changes reality or what sound there is.
So basically, we're going to need to have special speakers to even access that, right? When you say how you listen, I guess it's one hand our mental state, how you listen, but also what is the device that we listen through?
So the way that I think about it is that in the future, when quantum computers are developed, that would also lead to new sound technologies as well. So you could imagine having a system where the quantum computer is simulating phonons, and then the speaker is dynamically responding to its environment, so the observer or the person trying to see, like Alice in Wonderland there, trying to see what the quantum is. So what I think people can take away is that there will be new technologies coming through quantum computing and others that will allow us to start to hear and touch and get close to, say, the shadows in Plato's cave, the quantum world. And at the moment, I can't quite imagine what those are, but as soon as quantum computers are developed, that will allow other new technologies to be developed using the quantum computers as well. So there'll be a cascade effect.
Okay, maybe we zoom out for a second. So if all sound is a vibration, so what you're saying is that in outer space, for example, where we don't have any sounds at all, right? Can you explain that?
So in outer space is a vacuum. There's no material particles. And to have sound, whether that's like Newtonian sound or quantum sound, you need a transmitting substance, you need a medium for for audible sound or sound that can be detected. So in outer space, you just hear silence. So if you scream in outer space, it's just silent.
So there is no quantum mechanics in outer space, it's only in Newtonian, but it's actually not Newtonian?
So in outer space, you'll have light, so you'd have quantum of light. And when I mean light, I mean all different types of light. So like ultraviolet and radio waves and any sort of electromagnetic waves, radiation, yeah. But you don't have material particles in space unless you're within like the atmosphere of a planet or something like this, yeah.
Can you speak more to the idea of the temporalities that are happening at the same time, but also, as you said, the sound that is happening or not happening at the same time, the layering of that?
Yeah. So in the example that I gave, there's 5 atoms, and all of those 5 atoms are vibrating different ways at once, and that's superposition. So you would hear an intersection of different frequencies. I don't know how that would sound because you'll have effects like quantum coherence, quantum interference. But those different frequencies, so that would be if you're in the system, if you're measuring it one way. But overall, those different layers of reality add up to give no sound. So if you're outside the system, not inside it, you will hear nothing. But if you can dig into it, then you start to hear something else. So it depends on perspective, and it depends on how you listen. Then you will hear different things.
So to some degree, to be outside of the system is like the quantum collapse,
Yeah.
the materizing state.
Yeah. So the outside of the system is like thinking from the point of view of quantum measurement, and inside the system is thinking from like the multiverse or the many worlds perspective. So depending on how you look at the system or how you can interpret it or listen to it in this case, then you hear something different. And those possibilities exist at the same time within the sound. It is kind of mind-blowing.
It is, yeah. It's very hard to grasp.
It is hard to grasp.
And I wonder, do you think there could be any music or melody or composition in the traditional way that we know it coming out of those sound structures
the
or systems?
phonons, or I think so, yeah. I think because what the example I gave was a very small example with 5 atoms, but in larger, crystals can be huge. Like a grain of salt is huge compared to an atom. So then, of course, it will play. If that crystal was cooled down to absolute zero, the sound erupts automatically. The source is the medium. The source is just, it will play itself, and then it will play its own composition, which I think is really magical as well.
In such compositions, we're going to have a number of sounds simultaneously? Or?
Yeah. I mean, I guess the sound is a vibration, which is a frequency, and there'll be multiple frequencies at once. But I think the important thing is that it will probably hold different compositions all at the same time until we make a measurement. So that's a quantum collapse, and then we'll bring certain compositions into being. Yeah. So how we listen will really determine what we hear. Yeah.
I would love to see the rock band that is working with these sounds.
Yeah.
So before we take some questions from the audience, and please don't be shy, I am asking stupid questions as well, so it's really ungraspable. I want to ask you, as much as you know, what do you think is the future of quantum computing, and why is it good even? Why do we need that? Clearly, we need to cool down those systems, and that's very energy consuming. So what's the benefit of even creating quantum computing outside of the weaponized industry, the industry of weapons?
I mean, first of all, the energy, Carolyn and I were talking about this just before the talk. The energy is high at the moment because we need to cool the system down. But once full-scale quantum computers exist, and what I mean by that are the ones that can do any problem or solve solve the problems that quantum computers can solve, then actually the energy is much less than the big server farms that Amazon or Google have, because quantum computing will be way more efficient when it's fully developed. At the moment, it's really energy intensive because it doesn't really work. Yeah. But I think in the future, quantum computers are exciting for me because they allow us to explore the non-binary nature of reality. They allow us easy access to all different types of quantum phenomena, so superposition, entanglement. Because I program IBM's quantum computers across the cloud, and anyone in this room could create an account for IBM's quantum systems, and at the moment you get 10 minutes free a month. It's not a lot, but it's something. And you can code it yourself and have a go on it, etc. So I think that gives us access. You don't need to make a partnership with a scientist in a lab, which can be complicated. In terms of like applications that are beneficial, I feel like quantum computers are very good at simulating other quantum systems. Like I mentioned, simulating phonons, but they can simulate molecules or anything where there's atoms and molecules. And that means there'll be new generations of materials, drug design, biomimicry, so you'll be able to understand in detail how things like photosynthesis work, other biological systems. A scientist at Oxford recently told me she thought quantum computers would solve a problem of consciousness. I'm not so sure, but she knows more than me. So I feel like they're very good at understanding these other systems at a depth. Finally, something that I've been thinking about is a future quantum computer vision. So quantum AI, so not AI as you know it, a different version that can run on quantum computers. It's very, very different, but it still has some learning and so on. That will be able to start to see the world and our place in it as quantum. So at the moment, we're sensing reality using Newtonian tools. But when we start sensing reality using quantum tools, will we start to see that actually entities are more, life is more entangled than we even realize? That we can't see at the moment because we don't have the technology to see these things. So will we realize, it sounds very hippie, but are we all connected? And I think that, I don't know if that will be in my lifetime, I hope it is. But I think this changing our mindset away from the binary, away from the Newtonian, and into something that's non-binary, plural, entangled, will really help us understand our relation to nature and other systems in new ways. And that's the most exciting thing for me. Yeah.
I agree. Thank you. It was fascinating. Shall we take some questions from the audience?
질문 있으신 분 손 들어주시면 마이크 가져다 드리겠습니다.
Hi, thank you for the talk. I really enjoyed it. I have a question about the direction of vibration of the phonons, because I know that it's in quantum physics a bit like that. You can split things by their direction of vibration, and in sound it's always moving like this. So I was wondering about in which direction they would vibrate.
Exactly, it's still it's called longitudinal.
Okay.
It's still like this, so along the direction of oscillation. I'm just going to put my microphone down and use both hands to gesture here. Hang on, one atom could be moving, for instance, like this at the same time. Yeah. But always in the same way as traditional sound, but with each atom is vibrating in multiple directions at once, causing multiple different waves to build up.
And could you then split the different frequencies from each other through a filter?
Yeah, you can transform. Yeah, you can. That's possible. Yeah, 100%. But it's more complicated than Newtonian traditional sound. But you can transform a system to understand it in frequency. Yeah.
Okay, thank you.
Thank you for trying to convey all this complexity. I was thinking as you were talking, would it be possible in this quantum world that we start to perceive not through the eardrums, but on a more distributed level? Like if there's a quantum sound that is coming towards us, we don't necessarily hear it in a traditional way, but it's our all molecular composition that vibrates and resonates with the quantum sound. So is this something that's gonna unfold beyond the organs that coordinate our perception in the Newtonian world?
I love this question. I think it's really imaginative, and I feel like at the moment, if I was putting my scientist hat on, which I have today, I would say there's always this process of translation back from the quantum back to this reality. So then you'd perceive it more like traditional sound, but like I was saying, in the future, when there's quantum technologies like quantum computing, you could imagine a technology that could entangle quantum sound to our own molecular systems, which could be skin or something like this. Who knows? I'm totally speculating here. But for instance, I know some scientists have written about quantum brain-computer interfaces. So I don't see why you can't have a quantum sound interface where you're really entangling different things together under certain conditions. But we'll find out this when new technologies are developed, yeah.
My question is a bit abstract, so however this makes sense to you.
I love abstract, yeah.
Do you feel the future of our understanding of the whole quantum realm, let's say, is more or less a hopeful future?
I'm ambivalent. I know that certain big tech companies are working with quantum computing. I mean, it's highly entangled with the military in different ways. Also, certain companies are wanting to use full-scale quantum computers to expedite oil drilling and exploration. I mean, so there's, like any new technology, it depends on how we choose to use it. And at the moment, the history of big tech and how they've deployed AI and the ethics around AI suggests that the way quantum technology will be deployed might be similar. So we can imagine a quantum surveillance capitalism, etc. Sadly, I'd like to be more optimistic, but we live in a capitalist society and we know what happens, don't we, then?
But perhaps there's a possibility also that as the understanding unfolds, so does the whole relationship to everything, maybe.
That's what I would hope. This is what I was saying with Noam. This is what I would hope. So it could, I really think when quantum computers develop, it could be like a Copernicus moment where we remove ourselves from the center even more, and we see our connection and interrelation to other things. But of course, it's the way I see how big tech are using these tools are very like in a linear extractive mode. Whereas what we need is people like artists, curators, designers, everyone else, to be talking about these things, even though they're really difficult things to understand, to be talking about the sort of non-binariness, the magicalness of quantum. So then people understand the potentialities, because if we leave it up to big tech, I think we won't get that. They're just obsessed with money, aren't they? So I don't know. I mean, this is why I'm quite interested in giving a lot of talks around these topics and seeing how it lands with different people. Maybe I inspire someone else to do some work on these things as well.
Thank you.
Well, sadly, I only have the timetable in Korean, but I think we're right. Yeah. So thank you so much, Libby. And I'll invite Jungwon to kick us off with the next speaker. Thank you so much.
Thank you. Thanks, Noam.